Hello everyone, it is joined by Batunde Bukola again for our channel Nubira Process Designers, and I'm back again after a long period of time of break. So I am releasing a new batch of videos on tutorial and training on process engineering design with simulation software like Aspen HYSYS, Aspen Plus, AutoCAD Plus, Plan 3D, AutoCAD PNID, and chemical engineering design software. I'm going to be working with the software to design process plants, and I took a break because I was working on some projects. So now I'm back again, so I'll be able to actually share my knowledge with you guys. So stay tuned. Thank you for always the comments and the message that you have been sending. I really appreciate it. So and I'm very glad to share my knowledge with you guys. So today I am going to be working on an hydraulic tray design on a distillation column. So if you want to design a tray or a pack distillation column, so you want to design the packing heights and you just want a preliminary design with the simulation, material balance and energy balance simulation that you have done with the software, and you want to calculate a tray design or hydraulic design for the column based on the material balance result that you like after you converge the distillation column in Aspen HYSYS. You want to design the hydraulic tray for the column that will be sufficient and will not be, there won't be any inefficiency. There will be perfect mixing of the vapor and the liquid stream to ensure equilibrium before the streams leave the stage, so the column will be more efficient. So and that's what we are trying to design, and there won't be any weeping or flooding incidents in, and the operation of the steady state operation of the column will be steady, and it will be you can easily control the column if you design the hydraulic tray efficiently. So that's what we are going to be working on today. So today we have like a naphtha splitting unit for a refinery. So and we are trying to, we have three columns. This one is naphtha, the pentanizer, while this is the naphtha splitter, and the last one is the light cycle naphtha splitter, because this is this is another stream. This is naphtha stream, that's gotten from the crude distillation units. So and you are now concentrating the pentane content of the naphtha. So that's the meaning of the pentanizer that you have in the first column. And for example, this is material stream. This is there is no vapor stream in the column. With the configuration, is just a liquid distillate and it's taken from another stage, like it's not stage one, I think it's not the first stage, maybe the third stage. So you can see this contain high concentration of pentane and normal pentane, isopentane and normal pentane. Then you have some butane, you understand? So and the remaining naphtha is taken here. Then you split the remaining naphtha into two more components that we have. We have mostly pentane in this many pentane that we have, and hexane, some hexane here. Then this will be more like more heavy components, and you have the many heavy component of the naphtha stream over here: benzene, heptane, and to like nonane or octane. So that's the naphtha splitter, so you can use both of the stream in subsequent units in the refinery. And for the cycle naphtha, the same thing. We have the components, a pentane, hexane. Then for the heavy components, you have the second stream of the light cycle naphtha from distillation column. So we have this benzene and heptane and other higher hydrocarbon for the remaining one. So in this case, what we are actually designing is the tray hydraulic, and before you can design the tray hydraulic for any column, you must fully converge the column, and you must see, when you converge it, you see a green sign at the status bar at the bottom here. Then you have a pressure profile that will be later changed. You can make it to be isobaric, that is a uniform pressure. Later there will be pressure drop configuration that you can recalculate the column and make sure that the hydraulic result tally with the column material balance results. So you have the flow sheet, and for example, you can see the vapor stream and the liquid stream, or if you want to see better, you can go to the performance. You'll see the column profile for the hydraulic results, like to calculate the net vapor flow and the net liquid flow through each stage. Then you can see it is from the boiler stage to the uppermost stage, which is stage 30, and you have the stream draw and all those kind of things that is there, and you have the energy flow in each of the each of the stages is also there, so you can use it as initial estimate starting your tray hydraulic design. Then we have okay, I think that's everything. So after you have converged your column with the monitor tab over here, after it is everything is converged and you set the temperature profile and the pressure and the flow profile, you are able to get what you want for the column material balance. The next thing is go to internal. So this is where you are going to design your tray for your column. The internal, although there is a tray sizing manager in some old version of Aspen HYSYS, but those have been retired now. So you use the column design. Once you actually get to this place, you see something like okay, let me click on this. Okay, you see something like column design. You can see something like this interface. So you have internal manager that you can use, hydraulic plots. I'll be explaining that later. And once you are able to click, so we are using a column design analysis through in Aspen HYSYS now to design column. I think is more accurate and better than the old one. So, and you can size the column either using two methods, the rating method or interactive sizing. In rating method, you already know the column tray sizing and the data for the column tray, but you want to actually check the performance of you want to calculate based on the sizing that you know, the sizing data, the performance of the column at that, using that sizing data. So but for interactive, it's more like you are designing a new column and you want it to be interactive, like you are going to be starting with a default value that you can adjust to get or tune to the right value till you get a reasonable value that you are able to get a good result. And each of the variables, like the parameters, the tray sizing data parameters, will be related based on like the heuristic, heuristic relationship. Like for example, the tray sizing will be related to the tray diameter will be related to the tray spacing based on the normal ratio of tray sizing and spacing. Although you can override this, you understand, or you can use that as initial estimate. So interactive sizing is when you don't have enough information and you want to start from scratch, and you want to get a very good result in the design, in the designing of the hydraulic design. So, and you can also generate a data from using this auto section of the column, or you add a new one by yourself. So I'm going to generate a data for tray sizing using auto selection based on the flow that has been calculated from the column design. So, or I can generate it from feed and draw location, but on the best instance is using the flow, because it's the flow that will determine if there is going to be flooding or not in the column design, you understand. So, but the draw is mostly, it's going to partition the column into different sections, and it's not going to be realistic column design. You only partition a column design when it is very required, you understand. You can't find another way, you understand. But if you have a straight run column, it will be very easy to build, to manufacture in the yard or something, you understand. So you don't want to create problem for yourself. So, and I'm going to use this, then I'm going to adjust the sizing when it is done. So even using the flow, it is still partitioning into two. So I'm going to start with the minimum diameter for overall, because I don't, like I said, I don't want different sections. I just want one section. So I'm going to remove one section from it. And even you can see the result of the calculation, because the calculation is instantaneous. There's still some warning that I have to check and understand. Maybe I can remove the warning, so that maybe the column is operating as like a threshold point, like a delicate point to this stable condition, stable area, you understand. So I'm going to remove the warnings. So, and we have the sections. So for the sections, I'm going to remove the one with high diameter and add the end stage to be equal to stage 1, so there is no space on the column again. So you have the one with high diameter, and we still have the warning. So I'm going to check this section that I've just done and check if I can adjust anything from the tray sizing parameters. So here's the tray sizing parameters. We have the internal type, either tray or packed. For we are using a tray column. If I'm designing for a packed column, I'm going to pick this. So this is for a packed column, and I'm going to size the packing height, the section height, section packed height. I'm going to put it, or I pick packed height per stage, which is this. So it's going to show me the packing height part. It's going to calculate the section pack height, because I'm using interactive sizing, like I said. But if it is written, I have to put all the parameters. I have to put all the parameters there. So, and we have this interactive sizing. So then I'm going to go to tray, because I want to use tray. Then this is the area to specify for tray. You specify the type of tray that you're using, which is a bubble cap, which is a ballast or other special tray design. The numbers of pass in the tray section, liquid pass in the, like the downcomer pass. So for example, we are using 2. This is 2 going down, and 3. This is 4. We have one side wear, one center wear, and one off center wear. You understand? So this is 4 pass. You can see this sectional view over here for the numbers of pass, and this is the O diameter. You can adjust it, but this is the standard one, you understand. So you don't want to get it. So we have the O area per active area. You can use it to calculate the numbers of O. Then we have the downcomer rates. We have the side wear. We have the side downcomer and the diameter, which is this. So this is for the wear design. If there are some special configuration of the wired, and you can check those. can check those kind of picketed. You can see all these kind of pickets and swept back well designed. So you can we specify more parameters for the picketed and swept back wells, like the length, the picketed fraction, and the maximum loading available. It's just like when you have a drawback. For example, the swept back is when you allow space in between. You don't maximize all the space in the active area of the tray. So you sweep back some of the liquid hold up, you understand, so that you reduce the liquid hold up in the tray, you understand. So that's the meaning of the picketed and the swept back. And the picketed is just like having a regular shape or something. So and we have it. So I'm just using the standard one. That's why I just put none here. So then you have the geometric summary, which is the summary of what you have written in the geometric page. So you have the type, it's just like a results page for what you have written, and you can print it. And or although there's a way, multiple way that you can print your hydraulic design, I'll be explaining that. So we have the design parameters that is used for the interactive sizing. So you can use this like maximum acceptable pressure drop that is accessible in the column design. If it is more than that, it's going to return error. So you can easily look into the design and get it done. So you can adjust this, you understand, and to help your work to be accurate. So you have the maximum jet load float, maximum percentage liquid entrainment, minimum wear loading, and the maximum wear loading, the amount of liquid that must be on the wired wed before, so that there is no flooding or whipping. Then we have the warning status percentage to limit, then the sign factors too. You have the sizing criterion, all this kind of thing is there. So this one is for to help check the standard stable condition in the hydraulic plots and the limits. This is for the sizing criterion. Then we have the calculation method for whipping, for jet flooding, and maximum downcomer loading. So and you have the section efficiency. So if you want to keep any notes in this area, you can actually put it there too. So this is where you see the results of the column of the analysis that you are doing for the tray. So you have the start page and the ending page, some of the results too, and the result of the jet flooding that you are getting currently for the calculation that you are doing on the, and from the specification that you did in the geometric page over here. So you are going to see the results on this page. Then the tray results, you can see the hydraulic result of the tray in this page. So you can see the jet fluid, the dry pressure, and the downcomer backup, and the rest for the column. And you can see the center downcomer choke flow, the off center downcomer results, and the rest. You can see them, the hydraulic results, shots, and static condition, and physical properties, liquid, molecular, and the rest. So here is where we are going to see the warning. So the warning is saying that the downcomer area is 25% of best practice. So we want to increase the section diameter so that the downcomer area will not take most of the active area, so we can get more active area in the columns. Then we have the side downcomer exit velocity for tray 1 to 13 is greater than 0.56 meter per second. We recommend increasing the tray spacing or downcomer clearance. Okay, one of those two things. So and so I'm going to increase the diameter to be 6.52. Let's see. So just for a start, so we are getting whipping. So I have to try and get a lower number, maybe just 5.23. Okay, it's back to where I started from. So it's going to be in between 5.23 and 6.52. But let's increase the tray spacing to a little bit, 0.8. Let's see what's the value that was there before. 0.898. Just why 0.2 to it. 0.8096. 0.8096. Let's see the results from here. Whipping. Oh, let's reduce this 1.14. Oh, let's increase it 0.9096. So we're having whipping. So let's reduce the, let's put this one to be 0.08. So by decreasing the O area to active area, that is, we want to reduce the numbers of O that we're having, because whipping is actually caused when we have a lot of vapor, the pressure, they have a lot of vapor flow that is coming in the tray, and the liquid loading is lower, so there will be liquid entrainment in the vapor. That is, vapor will be carrying the liquid up off the tray, you know, instead of mixing with the liquid. So there will be some liquid that will be flowing on like against gravity in the tray. So we have that. So I'm going to check what happened. Okay, I think it is now working after reducing the numbers of O. So, and that means the vapor pressure will not be high to lift up the liquid in the tray again. So we have this this column is now okay. So we can now check the hydraulic plots to see the range that we are operating. Our current operating point was our current operating point. So everything is blue. When everything is blue, it means there is no error. When you see red, that is error. And I think when you see yellow, it's warning. So, and you have the vapor load and the liquid load in like the vapor flow rates and the minimum and maximum for each scale. You can see the range. So if it is very operating very close to the maximum, then it is not an, the best point is at the middle, but if you can get the middle, that will be very accurate for design, and this will also be at the middle here, you understand. So this one is for maximum entrainment, and this is the minimum point for 0% whipping, this 100% whipping, and this 100% jet flooding. So you have the constant vapor liquid plots here, and for each stage you have all the stage here, and you can go to stage with errors since there's no errors and warning, so everything is fine. So you can also go to the stage from here to, you understand, and see the operation condition for each of the stage and each of the points in the stage, like so, from 1 to 3, and you see the plot to in a schematic view, and the liquid is also there. You can see the liquid is also there. So, and after checking the plots, we are going to check the result too. For the results, you are going to check the approach to system limits. You can see 35.19, and the tray that is the maximum is 1.1 stage 1. So this is also very important. The numbers of pass, the tray spacing, all this design, tray with whipping, not, there is no whipping tray. So section height is also very important. If it's too large, then you have to reduce the section height, and the diameter too. If it is too large, you can reduce the diameter for the costing of the distillation column and everything, so that to make sure that you are getting a very sufficient tray sizing, and that is cost effective, you understand. So, and we have the tray spacing is 0.9096, which is not too far from the nominal value. So we have liquid molecular weight, vapor molecular weight, all these kind of things changing with the trail, and you can calculate them to. So this is for the physical property. You can see the hydraulic result too for each of the tray. So you can compare what we have in the summary, and you are going to get the right results. And just make sure that there's no message here, or the warning is something that you can simply ignore. So, and you have a way to start this tray sizing sectioning either from templates. You can export this as a template to your file. So you can click a file and open a XML file and save it so that you can send to another person that want to start a tray sizing analysis, a column design analysis with your template, with your tray sizing design, so the person can use it. So, and you can view the internal summary from this place. It's also the internal result from the distillation column that is exported from the internal page, internal spread over here. So, and you can duplicate it, this section again, you understand, and check the result, then choose the one that you want to use. So, and for example, you have the pressure. No, the pressure profile for the column is actually specified by you, and but in order to use the internal results, for example this internal results, you have to calculate the pressure dot that the tray will the pressure dot that the tray will exert on the stream, that is the vapor stream and the liquid stream that is coming. You can do it, calculate it from the top or at the bottom, you understand, so that it should conform with the tray sizing results, you understand. So then you calculate, once you specify the pressure drop here, it will calculate the column material balance based on the standard, the mesh equation. Then you'll be able to get the result again, and the analysis will be done instantaneously with it. It gets integrated. Then you can check if you are seeing whipping again. You have to recalculate the column analysis again, you understand, so you get the right value for the pressure and the tray sizing analysis. So, and I'm going to do that now, but before I do that, I have to check something, because I didn't specify the pressure of the tray the last stage. I only specify the reboiler pressure. So I'm going to be removing the reboiler pressure, because I want to start the pressure calculation from the top, because that's very important for the what they call this, the phase equilibrium distribution of the components in the top stage. So we are specifying this 4-stage pressure, but we are going to calculate the pressure drop for the lower stage, so lower stages. So I'm going to export the pressure drop from the top. So it's going to be updating the lower stages pressure drop based on the pressure drop that is calculated here. For example, you can see the pressure drop in the results over here. So this is the head loss. Where is the head loss? Okay, millimeter. This is 355 millimeters. So then you can check the stage, each stage head loss. You can see total pressure drop of each stage is actually specified there. So this is what is going to use for the material balance of the column. So everything has been updated. So, and the column is converging again. So after this, you still check the internal again if there is any error. So there's no error. So, and everything has been updated. And even if you check the hydraulic results, you can check the hydraulic results in this place. So you still see that it is still within the operation point. So you can see it's still within the operation point, and you can go to other stages, it's still within the operation point. So you can go to other stages, still within the operation point, so you can get it done. So, and this is done for this column. The next thing is to generate reports, or you go to column environment and see. Okay, before you go to column environment, you have to do something. You have to export the result to rating tab of the column, that is the sizing tab of the column, because what you have done is just analysis of the of the column. That is, this is different from the calculation of the column, so you have to export this or send it to rating. You understand? Or if you have the data in rating, you can even start the calculation, initialize the calculation of the analysis from the rating. So rating is like you have the results. Now you want to specify it for the column, so you have sent it to the rating now. So you can go to the rating tab of the column to see the results. So you have the sieve, the diameter, the packing space, the tray space, and the packing height, something like that. So the volume of the pack or the tray volume. Then you have all this kind of calculation for the column. Then you have the other vessels to the reboiler. This one is just the default value for the sizing of the reboiler. You have to size it for yourself. You understand? When you are designing the reboiler, the diameter, the length, and the orientation. Or for more detailed information on the reboiler and the tray, you can go to the column environment and go to the internals or rating for the tower, because this is actually the tower here. Okay, wait, this is not the tower. This is for the column. This is a column runner. This is the tower. You go to the tower over here, you can see tower, main tower. Then you go to rating for the main tower. You see everything here. You can see the sizing for the tower, the whipping, the diameter, the tray space, which is for the heights. So uniform one, because I specified the uniform one, that's why if you have a non-uniform data, you have it here, or you can quick size it. So then you have the type, which is sieve. Then you have the nozzles for the stages and for the feed and the product nozzle. So this is the feed nozzle and this is the product nozzle. This is the elevation. So for each of the stages, you have the nozzle here too, if you are using it or not. So you have the heat loss calculation if you want to model heat calculation for each of the stages, but since we are not working on it. So this is the pressure drop. So you can see the pressure drop here, and the total pressure drop is 18.63 kilopascal. You understand? So, and that's reasonable amount. So that's very, very important to get. Then for the reboiler, you can size the reboiler by going to the reboiler here and going to parameters. Okay, rating. Then you specify the type of shape and the sizing data for the reboiler. So you can use it in dynamic simulation or analysis, but once you have to do the tray sizing to do the dynamic simulation or analysis. So, and for the report generation, to generate reports, you have to go to this place. Once you have specified the tray sizing, this will be blue. You can see this one, there is no tray sizing, that's why it is gray. So it means it is okay, you have done the tray sizing for it, and you can easily go to the tray sizing by clicking on this page, and you see the column design too. So you can see reports here, so you can generate a report of the tray sizing from this, and you have the profile, all those kind of results that we get, the hydraulic plots, the design parameter that we use, and the tray and stage result that we use. So you can generate them. In PDF that you can send to your boss. Or send to anybody. And we also have this. We also have this export to vendor. Also have this export to vendor. You can export the result to specialized or column internal vendor packages like KG Tower. column and sourcing, I think like a sourcing distillation column, like a sulfur recovery column or something. Then we have the XML file for this kind of vendor to, so you can export it and you can continue your detailed analysis with the result that is got from the Aspen HYSYS. So, and I think that's the same method that we use for the res column. So, and I think we are able to, I'm able to explain in this short video like the concept of the tray hydraulic design with Aspen HYSYS software, and you are able to you'll be able to understand how to use it, how to use the concept in Aspen HYSYS and how to use it to design your distillation column, hydraulic tray, or packing in Aspen HYSYS. Is very simple and straightforward. So if you have any question concerning this, you can drop a comment on this video, or you can send me a message on numbera@gmail.com. and if you have any research or projects on Aspen HYSYS and you need my assistance, you can also call me. I'll be available to work on a project with you. And thank you for your time, and I really appreciate your time. So stay tuned to our channel, and you can also send us message if you want us to work on a topic. You can send us message on the topic on Aspen HYSYS that you want us to work on. We'll be glad to hear the message, and we can, because I'm currently back now, so I'll be glad to work on any video and release it to the public. So thank you very much for your time. I really appreciate. Stay tuned.